information can produce. So this range of spectrum in our machine is from the infrared, so the X to the X-ray. So from the fractions of the molecular structure from the biological samples until the atomic structures of the materials that we can detect and give the information. So this range of spectrum in our machine is from the infrared, machine, so the X to the X-ray. So from the fractions of the for us as well, molecular also this is structure called from the biological sample until the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. So from the fractions of the for us as well, molecular also this is structure called from the biological sample until the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. So from the fractions of the for us as well, molecular also this is structure called from the biological sample until the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. So from the fractions of the for us as well, molecular also this is structure called from the biological sample until the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. So from the fractions of the for us as well, molecular also this is structure called from the biological sample until the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. So from the fractions of the for us as well, molecular also this is structure called from the biological sample until the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. So from the fractions of the for us as well, molecular also this is structure called from the biological sample until the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. So from the fraction biological sample until the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. So from the fraction for researchers to use. To the atomic spectrum in our machine is from the infrared machine, so the X to the X-ray. All of the design of the storage ring and insertion device include the bending magnet, including the undulator, including the wiggler and wavelength shifter. We have 12 beam lines, 12 end stations like this in the schematic. And available techniques, we have all of the design of the storage ring and insertion device, including the bending magnet, including the and we have the photo emission techniques. So we have 12 beam lines, 12 end stations. like this in this schematic. And available techniques, we have all of the design of the storage ring and insulation device, including bending magnet, and we have the photo emission techniques. So we have 12 beam lines, 12 in the HES, like this in this schematic. And available techniques, we have all of the design of the storage ring and insulation device, including bending magnet, and we have the photo emission techniques. So we have 12 beam lines, 12 in the HES, like this in this schematic. And available techniques, we have all of the design of the storage ring and insulation device, including bending magnet, and we have the photo emission techniques. So we have 12 beam lines, 12 in the HES, like this in this schematic. And available techniques, we have all of the design of the storage ring and insulation device, including bending magnet, and we have the photo emission techniques. So we have 12 beam lines, 12 in the HES, like this in this schematic. And available techniques, we have all of the design of the storage ring and insulation device, including bending magnet, and we have the photo emission techniques. So we have 12 beam lines, 12 in the HES, like this in this schematic. And available we have all of the design of the storage ring and insulation device, including bending magnet, and we have the photo emission techniques. So we have also HES. So this 11 hour per shift. We start from 8 o'clock in the morning and we finish the first shift about 8 p.m. and then we start 9 p.m. again until the 8 p.m. in the morning again. So we give the injection time about 30 minutes actually in the daily life. This is the image of the technique according to the list that I mentioned already. So we have beamline 1.1, 1.2, 1.3 until beamline number 8. So it's named as the number of the bending magnet at that port. But if we have the alphabet behind the number, that means that beamline that produce the synchrotrons from the insertion device. W is mean wiggler. U that mean undulator. So some kind like this. You can go to the website for more information, www.sri.or.th, to gain the details about all the beamlines and techniques and specification that we can use. So this is the basic schematic of the beamline by its optic elements. So this is a source to produce synchrotron that's come out from the machine via apertures. We have slits. We have a CM mirror to collimate the mirror. Collimate the beams. And then we have some kind of monochromator to choose the energies that you want to use in your experiment, and then try to deliver the synchrotron light to the experimental station. While you set up, you put the samples in, and you have the detector to detect any signals that you want and interpret all of the data from your detector to be the information from your samples. So via the graphic like this, we mentioned about the booster ring, storage ring already. And then when you deliver the synchrotron through the optic elements, we call it beam lines. And you have the end station and user area that to prepare the sample and put the sample here at the end station. Let's get to the techniques. I try to group the technique, 12 techniques together. I try to group it together. The first one, we're talking about the techniques that concerning about the scattering interactions. So the scattering interaction, what we can do, you strike the synchrotron through the sample in this small red things is your sample, and we are passing through the X-ray, the vacuum tubes to the detector, the 2D detector. You get the pattern of scattering. In these pattern scatterings contain the kinds of information like you can do the diffraction patterns. So if you track this pattern, you get this pattern like this, you track the intensity in these radial directions, you can get the information like the XRD, the X-ray diffraction, but it's 2D. So there's some kind of interpretations of the mathematic circular integral in this direction, and you get this graph. It's pretty as an XRD result. But if your sample is not that much crystalline things, you can get the asymmetric pattern. It's not the complete rings of the circular rings. You can get asymmetric patterns. And if you interpret the asymmetric pattern, you can get the bigger structure, more than the atomic structures of the XRD. You get into the range of the hundreds nanometer scale until the sub micron scales by this interpret this pattern, asymmetric patterns. And also the diffraction patterns, well, you have the techniques. There's diffractions again, there's a protein crystallography that we have. I'm gonna skip this technique today because we want to talk about the materials. The other interactions, the concerning is the absorptions. So if you put a sample like this, you try to detect the synchrotron radiation that before it passing through the samples and after it passing through the samples, and you compare this amount of X-ray that's passing through, you will get the spectrum amount while you change the energy that you're striking through the sample. We call it the absorption spectra. By this absorption spectra, it jump up on the energies that mentioned in the table that and tell you that what elements for this edge. And for example, this is the edge of the copper. And while if you deeper analyze the shape of this spectra, you can tell you that around the copper, what is the atoms around the copper and how far of it. So you can make up atomic structure from this information. This spectrum, we have the two range called SANS, X-ray absorption near edge spectroscopy, and the extended range we call the XR. By these both, these tell you the elements and what is around. By the XR regions, it tells you the scattering pattern, forth and back. So you by this pattern, you interpret it out, you get the bond length and bond angles, atomic structure of the samples around the edge. Our beam line, we have about roughly 3 to 4 beam lines in absorption techniques, and all of the elements we can detect like this. So in the periodic table, we can detect from calcium up to the zirconium in this beam line and up to arsenic in this beam line. And by the transition metal or noble metal like this, and via the lanthanide and actinide, some of them in this beam line. And this beam line also detect a lot as well. So most of the elements in periodic table, if it's not that too light, like the lithium, or if it's not that too heavy, we can detect it via our machine. When you get the absorption phenomena, you can get the fluorescent phenomena as well. So by the fluorescent, the electron jump up and release down and release the fluorescent X-ray out. It show you the information of the elements that contained in the sample. But a good point in the synchrotron facility, you can focus the beam. So when you focus the beam to be small and you track the beam along your sample, you can do the mapping of the element in your sample. For example, this is a potteries, ancient potteries, and have the painting on top of the surface. And it is on top of the surface when you do the detect of the iron elements and scan the beam along the samples. You can see the distribution of iron here like this. And this is an example of the distribution of the titanium. So by this information, you can conclude that by the painting, the red painting like this, the pigment, they use iron, especially iron oxide, to be the red pigment in the ancient potteries. We also have the photo emission techniques. So actually, if you let the synchrotron strike through your surface of the sample, you will get the emission electrons come out. And by this emission electron, if you get it passed through the energy dispersive, you can gain a picture while contain the information of electrons. And by that, you can interpret it up like the XPS technique. And by via the data like the XPS technique, you can distinguish the state of the elements you have. in the sample like titanium dioxide, TiO2 or Ti2O3 by the deconvoluting this graph like this. And you can determine the binding energies, like even though that you can detect all of your sample is carbon, but you can interpret that is a carbon, hydrogenated carbon, or carbon-carbon interactions, carbon-chlorine, carbon-fluorine, fluorinated carbon, or carbon-oxygen. These design techniques are, we strike through the synchrotron, we put the samples here, we rotate, and we get the image of each plane and reconstruct all the image again. We get the 3Ds of the image. It's very useful. It's an imaging technique and one like this. I will skip this IR techniques because mostly it's concerned about the biological samples. Last but not least, we have the lithography technique, which is very useful. So you can craft up small patterns and craft up the small lab on the chip, and you can use it later on in your experiment. It's very useful. You can craft up the small sensors, small heaters, or small actuators by this technique. Finally, we also have the supercomputer. We have the Computational Science and Engineering Center. I'm looking after this section as well. We have the cluster that can compute the information with 200 cores roughly. That data storage roughly we have 150 terabytes. So we use these facilities supported the synchrotron research to interpret do modeling of the information that do the experiment by synchrotron. Let's get to the example. I think we have the few minutes left. I'll go quick. This interesting work come from the researchers try to fabricate up the aluminum nitride film. So we are the fabricate aluminum nitride film that use sputtering techniques, RF sputtering, while the substrate they use just only the lime glass. So the amorphous of the lime glass structure, that means you cannot control the structure of the film at all. However, when you feed up the nitrogen gas in the chamber in the different various content, 20 to 80, the film when you are characterized by XRD, you gain the different structures come up. So it's strange. It seems like by controlling the numbers of the gas content in the sputtering chambers, you can control the structure, which is surprising. When we use AFM, we use SEM, we see the different structure, it's different content of nitrogen gas. Here it's like the horizontal structure, while here is like the vertical structure. By FE-SEM, it's quite clear that you get like a needle structure on the surface. Then we use a synchrotron radiation technique. Here we use the absorption techniques. We get the spectrum, and if you diagonalize the samples a little bit and rotate it, you can see that the feature of the spectrum that change. That means your synchrotron radiation detects some structure in the horizontal structure more than the vertical structure. And by this information, as sum up like we have the different the direction of the structure growing on the surface. We end up this work by doing the modeling by the supercomputers. We start up with the structure of aluminum nitride. We try to aluminum vacancy in aluminum nitride film or nitrogen-rich conditions and different plane, and then we come up with the different energy formation of each surface. So that sum up with the conclusion of this work that while we are in the situation that we lack of nitrogen or we rich of nitrogen, the film like to grow in different direction, different plane. That's why you get a different structure. So by this information that's published in the Journal of Alloy and Compound, it concludes that you can architecture your structure while you don't need to use the expensive substrate like silicon, high-grade silicon. You can use amorphous things, but just feed the gas, nitrogen gas. So it's much cheaper to set up the experiment while you can architecture nanostructure of the film. The second research, let's talking about archaeologies. So we can read the past by synchrotron light. I bet in our region is rich of the artifact, the archaeological samples. We share the cultures together in the past so much, and this is a glass bead, ancient glass bead. It looks beautiful. It looks opaque in the yellow color. We choose only yellow color to study in this case. This is from the around this area in Thailand, about 200 kilometers away in the site, and a geometrical site is like this. So we have the 4 archaeological sites, and if you dig down, sorry, in the ground, you can see the cultures, the ancient cultures by this site. You can see potteries, you can see the glass beads ones. If we look at only the yellow ones in this case, if we track back to the literature review, these are all the yellow pigment in the ancient artifacts. We have the Latin yellow 1, Latin yellow 2, or Latin antimony pigments like this. So we use absorption technique as also fluorescent techniques to explore these glass beads. This is spectrum of the glass beads. We cannot detect any signals of the antimony. So let's dispute the type 3 of the pigment. We have the spectrum of the lead like this. We have spectrum of the tin like this, and it's pretty the same. So actually, we cannot sum up that it uses a type 1 or type 2 yet right now. But by the X-ray fluorescence, it said that it's a topaz glass. So if match up with the literature reviews about the culture study, these beads is imported from the Indian Empire in that time to this region, which is quite surprising, it's quite far. So this is information we can look in the past by synchron radiation. Do we have few more minutes?
I still have another 20 minutes.
Okay, let's get quick. The last examples. This is a work of the researchers try to synthesize the catalyst that absorb the mercury. So actually, basically, it's a titanium dioxide nanostructures doped with silver. And when they test the ability that absorb the mercury, is going very well. They do the absorption spectra. It can sum up that the silver that doped in titanium dioxide structure, it show up the 1+ charge. So the silver 1+ instead of silver neutral silver, silver 0, which is strange because they dope the silver 0 in, and silver will not interact with anything. So how we come up with the silver 1+? So there is a work as well about the theoretical population modeling, and they do the modeling like this of the cluster of the silver. Then the lowest of the numbers of cluster they can do is 13 atoms. They try to put the mercury in to see the absorption energies. However, they can conclude that why the silver that show up in the synchrotron spectra to be 1+. We do further work like this. So we simulate the structure of titanium dioxide here and the structure of the silver cluster here. But if we simulate the signal of the X-ray absorption via the scattering point at these atoms, the spectra come up to be different. And the reasons why, because the silver here has been in the influence of titanium. So electrons surround of the silver tends to go down than go up. And then it gives virtually the dipole of the atoms, these atoms. That's why when you try to detect the silver, the smaller one of the cluster, you can see more charge effect. The silver is going to be clearer to be 1+, while the silver on the top is the silver 0. So by simulations, we can solve it up. So this is a model of the when we get the answer of the why is get the 1+ charge. They comes up with the mechanisms to propose into the publication to the journal that this is a mechanism to absorb the mercury into the system and spilled out the mercury out into the titanium dioxide. So they publish in the good journal. So let me sum up. Today, I hope that in the audience, we get the idea of synchrotron radiations that's come up from the synchrotron source, which is, of course, accelerators. And I think you can get a good point why we have a chance, good opportunities why we use the synchrotron compared to the other lab source in the experiments. And the key feature of synchrotron technique, I hope that few of them will match up with your interest that you doing research about material science right now. And well, finally, work hard and keep young mind. And I will finish my talk with these things, the new things. I generate this picture from the Mid Journey. Some of you may know it already. It's an AI platform. So this picture, it doesn't take, I didn't take this picture from any camera. I just key the keyword in the grammar of the AI in that platform. And this picture comes up. So this is the new generations of the research about the machine learning and AI. So I will end up my talk like this. Thank you very much.
Okay, thank you very much, Dr. Butikrai, for your interesting presentation regarding about
Can't hear. Can't hear you.
Yeah, we can hear you. Hello. Yes. Thank you very much again, Dr. Butikrai, for your presentation. So we will have another discussion after the third speaker with our panelists. So we are going to our second keynote speaker, Dr. Sungyot. So before that, I will like to.
Anyone can hear me?
Yes,
Hello?
we can hear you. Yes, we can hear you.
I can't hear you at all.
Ah, really? Yeah. So before, we already have a screen from Dr. Sungyot. So maybe before that, I would like to can Dr. Remy, can you provide the slide for introducing the Dr. Sungyot? Hello. Or we can hello, Dr. Remy, can you provide the introduction slide for Dr. Sungyot? Hello.
Okay.
Okay.
Okay. Can hear you now. Sorry.
Okay. Before we start, can you enlarge it? So our second keynote speaker will have to be Dr. Sungyot Kaimala, PhD. He born at 15 July 1989. His occupation now is a postdoctoral researcher working on lithium-ion batteries and natrium-ion battery development in Institute of Nanomaterial Research and Innovation for Energy, INRI, Kokkan, University Thailand, from 2022 until now. His research about material science, and his working experience, he worked at 3 places before, as researcher at laboratory the reactive semi-des solides and at University Picardie Jules firms at France 2021. And he worked also in researcher at Institute of Nanomaterial Research and Innovation for Energy, INRI, Kokkan University, Thailand editor, and also become the Thailand editor principal investigator in chief Indonesia. I'm sorry, this is I think it misunderstand. And also the last is a short-term research program at laboratory of Professor Won-Sup Yeon in Sukkyukan University, Korea. I think he's also working with Synchrotron, also working with Psr, I think. And he has 1 patent about nanomaterial from rich husk for use as electrode and for lithium-ion batteries, April 24th April 2019. And he also get awards, 2 awards in and the winner of Thailand's New Gens Inventor Awards 2020 and also 2021. And it is quite interesting CV, I think. So I think after this one, Dr. Sung-hyuk, the floor is yours.
Okay, thank you for introducing me. And can you see my full screen right now?
Yeah, we can see your screen right now.
Okay. So, good morning, ladies and gentlemen. I am a representative from Lithium-Ounce Battery Research Group from Content University. Today, I am going to talk about X-ray absorption spectroscopy applied to battery materials. The topics of my presentations consist of 3 material parts, including the overview of lithium-ounce battery. I will talk about the main components and working principle of lithium-ounce batteries. The next part is X-ray absorption spectroscopy for battery research. I will talk about our research related to X-ray absorption spectroscopy investigations. Finally, I will talk about I would like to introduce you to know Content University lithium-ion battery pilot plant. I believe everyone knows lithium-ion battery because we use them as energy storage in mobile phones, electric vehicle, and electronics device. Lithium-ion battery consists of 3 main parts. The first part is a cathode material such as lithium cobalt oxide, lithium nickel manganese oxides, and lithium iron phosphate. The second part is an anode material such as graphite, lithium titanium oxide, and tungsten metal oxide such as tin dioxide and silicon dioxide. The last part is an electrolyte material, which is lithium salt as lithium hexafluorophosphate in organic solvents such as ethylene carbonate and dimethyl carbonate. The figures demonstrate the working principle of lithium-ion battery. When the battery charged, lithium ions will be extracted from cathode to the anode. When the battery discharges, lithium ions will move back from anode to the anode. And this part, I would like to talk about common cathode material used in lithium-ion battery. The first material is a lithium cobalt oxide that has a radial structure type. The second material is lithium manganese oxide that has a spinel structure type. The last one is lithium iron phosphate that has an olivine structure type. The right figure shows the electrochemical movements of cathode material for lithium-ion battery. For example, lithium cobalt oxide cathode material exhibits low lifespan because of its structural instability. And the second material is NMC cathode material or lithium nickel manganese cobalt oxide, which is a next generation of lithium cobalt oxide cathode materials, reducing cobalt content and using nickel and manganese can improve the lifespan of the layer cathode material type. And I am talking about cathode material because the energy density and the cycling stability of lithium-ion battery are significantly determined by their cathode materials. Therefore, the understanding the structural property and electrochemical mechanism is a crucial key to develop the performance of lithium-ion batteries. So the and X-ray absorption spectroscopy is an useful technique to study cathode material for cathode and anode material for lithium-ion battery. Now let's move on to lithium. Let's move on to sodium. Let's move on to X-ray absorption spectroscopy for battery research. X-ray absorption spectroscopy has been used to study the local structural property and electrochemical mechanism of cathode material in rechargeable battery. This is because X-ray absorption spectroscopy is element specific by tuning the energy of X-ray to the absorption rate of an element of interest. This makes the local structure and electronic property of the selected elements can be investigated. Analysis of absorption age position and absorption age feature provide the information about oxidation state and size symmetry. Moreover, X-ray absorption spectroscopy can be used to study amorphous materials and small particles. And this part shows our research related to X-ray absorption spectroscopy investigations. We always use X-ray absorption spectroscopy techniques to investigate the structural property and electrochemical mechanism of electrode material for rechargeable battery. For example, this work we use in situ X-ray absorption spectroscopy to investigate the electrochemical mechanism of a transient phase in lithium-ion silicate cathode materials. Lithium-ion silicate cathode material offer high energy density and power energy density because more than one lithium is involved. In this study, we used in-situ X-ray absorption spectroscopy to investigate the electrochemical mechanism of lithium-ion silicate cathode materials. The experimental results show that the oxidation states of ions change from 2+ to 4+ during charging process. This indicates that 2 lithiums can be extracted from the structure of the lithium-ion silicate cathode material. This makes the cathode materials reveals high capacity density because more than one lithium is involved. In order to study the transient phase during cyclings, we cycle the battery and then we stop applying current to the battery cell as relaxation, as shown in the left figure. During the relaxation, we collected the same spectra as demonstrated in the right figure. There is a shift of ions KH energy, indicating a rearrangement of ions to form a transient phase. This study is the first time to investigate the existence of an transient phase during electrochemical cyclings by in-situ X-ray absorption spectroscopy. The next work, in this work, we use X-ray absorption spectroscopy to study the impacts of the manganese doping on the structural and electrochemical properties of lithium-ion silicate cathode materials. The right figure shows the Fourier transform X-ray spectra After fitting the exact spectra, we obtain the bond length of ions and oxygens. The results show that magnesium doped electrodes provide larger ions and oxygen bond length compared with the undoped sample. The larger ions and oxygen bond lengths can facilitate the lithium-ion diffusion in the structure, leading to improved race performance and high reversible capacity, as shown in the left figure. Now, let's move on to Lfp Catalyst Material or lithium-ion phosphate. The electrochemical mechanism of lithium-ion phosphate catalyst material related to the formation between lithium iron phosphates and iron phosphates. However, there are many previous work report that it is possible to have a dynamic phase during cycling at a high current rate to confirm the existence of a dynamic phase. This works, we use in situ X-ray absorption to study the electrochemical mechanism of lithium iron phosphate catalyst material during cycling at a high current rate. To study the dynamic phase during cycling, we cycle a battery at a high current rate, and then we stop applying the current to the battery cell as relaxation for 30 minutes, as shown in the left figure. During the relaxation, we correct same spectra as demonstrated in the right figure. As revealed in the figure, during relaxation, a shift of ions KH to higher energy corresponding to the metastable phase or dynamic phase. From delta mu plot, the increasing in delta mu amplitudes correspond to a metastable phase with a larger ions and oxygen bond length transform to stable phase, such as lithium iron phosphate and iron phosphate phases within 10 minutes. The often results indicate that X-ray absorption spectroscopy technique is an useful tool for investigation of dynamic phase, which is difficult to detect by another techniques. So let's move on to the next catalyst materials, which is layer catalyst materials. This catalyst material type is a composite between two catalyst materials that have layer structure type. This catalyst material type is called layer structure catalyst materials. The electrode material have high specific capacity. However, it exhibits structural transformation from a layer structure to a spinel structure during electrochemical cycling, leading to poor cycling stability and low energy density. The understanding the parameter that affects the structural transition behavior is an important thing to improve the electrochemical performance of the electrode material type. This work, we studied the impacts of lithium manganese domains size on the electrochemical property of a layer catalyst materials. A layer catalyst material are prepared by a solder method and solid state reaction method. The diffraction results show the cathode materials obtained from a solid state reactions exhibit larger phase separations. That's the cathodes obtained from the from the X-ray results. The cathode material obtained from solid state reactions exhibits a larger phase separation than the cathode materials obtained from the studio method. From the high resolution TM, we see that cathode material obtained from a solid state reaction had a larger lithium manganese oxide domain size than the cathode material obtained from a studio method. From same spectra, it indicates that the two cathode material have a same average local structure. And from the Fourier transform XR signal, we will see that the manganese and cobalt atoms in the two cathode material are surrounded by different number and type of transitions metal atoms because they have different degree of phase separations. This indicates that the X-ray absorption spectroscopy techniques can be used to study the phase separation behavior and differentiate the between the solid solution and the phase separation behavior in electrode materials. And from the electrochemical performance, as shown in the right figure, we will see that the cathode with a larger lithium manganese oxide domain size show the higher cycling stability than the electrode with a smaller lithium manganese oxide domain size. This is because a larger lithium manganese domain size can retard the phase transformation during prolonged cyclings. So let's move on to the next work. In this work, we study the effects of heating and cooling rates on the structural property of our layer cathode material by in situ X-ray absorption. The given figure shows the contour plot of same spectra corrected during heatings and coolings. The results show that at several heatings rate induced lower formation temperature, and from same spectra, it can be seen that heating conditions have no significant impacts on the local structural property of the obtained materials. And the left figure shows the high resolutions TM image show the heating condition have significant impact on the microstructural property of the obtained cathode materials, bringing about various lithium cobalt oxide and lithium manganese oxide domain size. A layer cathode material with suitable lithium manganese oxide domain size can reveal improved cycling stabilities. And this works into investigates the impacts of current rates on the structural change and cycling stability of a layer cathode material during prolonged cyclings. The TM image illustrates the cathode material is a composite material type because its one particle consists of the domains of lithium cobalt oxide and lithium manganese oxide phase. After 20 cycles, the electrode cycle at a slow rate exhibit a larger degree structural transformations from a layer structure to a spinel structure, as can be seen in the manganese KS same spectrums. In addition, the electron cycle at a slow rate reveal lower crystallinities compared with the electron cycle at higher rate. The left figure shows the differential capacity plot. Cycling at slow rates can induce larger lithium manganese activation, leading to larger level of manganese phase transitions. And electron cycle at a high rate revealed better cycling stability than the cathode cycle at slow rate. This is because a high rate can reduce the lithium manganese oxide activation and retard the manganese phase transition during cyclings. This reveals that electrode material is suitable for high-rate applications, such as electric vehicle. And let's move on to the new battery technology, which is aluminum ions. The interface properties between cathode material and electrolyte materials have impacts to the performance of lithium-ounce batteries. So this work, we aim to study the impacts of the concentration of electrolytes on the formation of a passivation layer or aluminum oxides on the surface of aluminum cathodes. The results show that from we use X-ray absorption spectroscopy technique to study the level of the formed aluminum oxide layer on the surface of aluminum electrodes upon electrolyte concentrations. At the highest electrolyte concentrations, the surface of aluminum electrodes is almost oxidized to form a thick aluminum oxide layer. Electrochemical reactions are difficult to occur for low electrolyte concentration. A high electrolyte concentration provides a thick layer oxides acting as an obstacle for occurring electrochemical reactions. And finally, an electrolyte concentration of 1.3 per 1 reveals that the electrochemical reaction is easily occur. This indicates that it is suitable for long-term of electrode stripping and cratings in lithium-ion battery. From our experimental results, it can be seen that a combination of X-ray absorption spectroscopy with another techniques, such as X-ray diffraction and high-resolution TEM or SEM, is a powerful strategy to develop and study electrode material for rechargeable batteries. That's all for example of our research related to X-ray absorption spectroscopy investigation. Konkan University has registered for many IPs related to multi-ion battery supply chains. We have many projects to achieve clean and sustainable energy storage. To translate this IP and research to practical applications, around 4 years ago, we obtained financial support from Thai government to construct a lithium-ion battery pilot plants at Konkan University, as demonstrated in the given figure. We are the first lithium-ion and sodium-ion battery cell producer in Thailand. We can produce battery cell with a total capacity of 2 megawatt-hour per year. Our products can be customizable. Finally, our products and managements are certificated by local and international standards. We are able to formulate chemistry and produce lithium-ion battery cell in Thailand, and we also have a partner in China to fit your need. This shows facility in the lithium-ion battery pilot plant at Konkan University. We have many battery tester and standard tester. That's all for my presentation.
Actually, we just have the first speaker is to talk about technology of the synchrotrons, and our second speaker talk about the application of the synchrotrons accelerator for the material calculation especially for battery materials, something like that. So will be our last but not least our keynote speaker from Indonesian side, our chairman for the research organizations for nanotechnology and advanced material, Dr. Ratno Nuryadi. Maybe I would like to talk about first. I want to introduce our third speakers. Dr. Emi, can we provide his personal data? So our third keynote speaker will be Professor Dr. Ratno Nuryadi. He is the chairman of the research organization for the nanotechnology and advanced materials BRIN Indonesia. He is a graduate from Shizuoka University at Research Institute of Electronics, and his research about nanomaterials engineering for high sensitivity sensor application for physics, nanoelectronics, and nanosensors, maybe quite is related to our synchrotron accelerators application. And he also get awards from Ahmad Bakri Award 2010 and most promising young scientist or Japan Society of Applied Science, Applied Physics. And also the last one, Adicipta Rekayasa for the Indonesian Engineer Association for PII. And also managed to organizing in IEEE member since 2012, and then also the chairman of the Institute of Science and Technology Studies Japan from 2006 and then 2008, and he also become the chairman of the Masyarakat Nano Indonesia and Masyarakat Ilmu Teknologi Indonesia, and also the last one is chairman of the Hipenindo Tangerang Selatan. His personal data maybe for his presentation will be talk about what kind of research that conduct in nanotechnology and advanced materials research organization. Also, what kind of research and development regarding about accelerators, synchrotrons. The floor is yours, Professor Dr. Ratno Nuryadi.
Thank you, Dr. Muhammad Rifai. Can you hear me?
Yes, we can hear your voice.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Distinguished Chairman of Research Organization for Nuclear Energy, Dr. Rohadi, distinguished Deputy, Dr. Edi Giri, distinguished speakers, Dr. Uti Krai Usayapon, and Dr. Sangyot Kaimala, distinguished panelists, Prof. Evi Kartini, Mr. Teguh Julius Surya, PhD, and Dr. Suci Winarsi. Ladies and gentlemen, first of all, thank you so much for inviting me to give speech in this mini symposium. It is my great pleasure and honor to be here. Indeed, this symposium is quite important and very useful for us, especially research in material science. So far, we still don't have synchrotron, but we can learn many things about the synchrotron radiation for material research from lectures and also from panelists. So after we follow two lectures from Dr. Wutikrai and Dr. Song Yut, allow me to present a little bit different side from synchrotron radiation. I would like to share my slide. Can you see this slide?
Yes, we can see your slide.
Okay. In this time, I would like to talk about the research activities and research organization for nanotechnology and material, especially potential material research for synchrotron measurement. So I would like to talk about the two items here. The first, the brief introduction about our research organization, and then the potential material research and research organization for nanotechnology and material for synchrotron measurement. Okay, for the introduction, as we know that last year in September 2021, according to Presidential Regulation number 78 2021, several research institute, Indonesian Institute of Science, LIPI, Agency for the Assessment and Application of Technology, BPPT, National Nuclear Energy Agency, Badan, and then Indonesian Space Agency, LAPAN, the Ministry of Research and Technology, and another research unit from ministry institution merged to the National Research and Innovation Agency, BRIN. So in Indonesia now only have one National Research and Innovation Agency, Research Institute. Okay, this is the structure of BRIN organization. As we know, there are 7 deputy here, and then we have 12 research organization, and one of the research organization is Research Organization for Nanotechnology and Material. So each research organization cover research center, and the number of research center in BRIN now 85 research center, and in research organization for nanotechnology and material have 7 research center. So this is the research center in nanotechnology and material. The first one is Research Center for Mining Technology, Research Center for Metallurgy, Research Center for Advanced Materials, Chemistry, Polymer Technology, Quantum Physics, and Research Center for Photonics. So we have several laboratory now. Laboratory in our research organization located at the 4 place. So in Lampung campus, and then in South Tangerang City campus, this most of laboratory in this location, and also in Bandung campus and Yogyakarta campus. So the most of laboratory and research center in South Tangerang City, and here this is close to the Jakarta city, just around 30 kilometers from the Jakarta. And this is the view of National Science and Technology Park in South Tangerang City, where our laboratory research center are located in this National Science and Technology Park. So this is the area of the Science Technology Park, and then 7 from 10 fields of national technology priority are located in this area. Okay, so our mission and research organization for nanotechnology and material to provide fundamental and applied material science research and problem solving for current and future needs of society. So we would like to have a contribution in the invention and innovation in key technology, produce new material using the ultimate technology, nanotechnology in here, and realize higher function for material. So we have target in the future to increase the utilization of local natural resources, increase in import substitution, and mastery of material technology and their application. So we have several strategy here, development resources for the achievement of research goal. Also, we would like to make the domestic and global collaboration, and then research collaboration center, and we also accept the visiting professor, visiting researcher, postdoctoral researcher, and also we push the PhD and master degree by research. So from the 7 research center and our research organization, as you know that our research term is very wide range from upstream here, from research in mineral, material and process technology, nanostructure, circuit and system technology, and also in various application in downstream application. So this is such kind of overview of research terms in our research organization. Many type of research in here, from the basic fundamental research in nanoscience, and also in the process synthesis and measurement, also in simulation theory, and some person also have research in the material design, function design, and for the several application in energy, life science, healthcare, environment, and also in ICT and electronic. Okay, let's enter to its research center. First, research center for mining technology. In this research center, we have 64 researchers. So in this research center, we have 4 research groups in the term of mining exploration, environmentally friendly mining, and then the increase in value added and techno-economic material, mining impact management. So we have several laboratory and research in here, not only in South Tangerang, but also the laboratory located at the Lampung City, Bandung, and also in Yogyakarta. So this is the research center for metallurgy. There are 4 research groups here in the field of special steel and alloy, corrosion and mitigation technology, extraction metallurgy, and primary secondary resources, and non-ferrous alloy and metal matrix composites. The third one is Research Center for Advanced Material. In this research center, we have 14 research groups, including the battery, high technology rubber, bioceramic, colloid nanoscience, creative functional ceramic, high resistant material, biocompatible material, photo conversion energy, fuel cell and hydrogen, low dimensional functional material, magnetic and superconductor, structural material and industry, thermoelectric material, and finally also a research group on surface and coating technology. So next, the research center for chemistry. We have 8 research groups, including the surface chemistry and nanoparticle, biochemistry, analytical chemistry, catalyst, nutraceutical and organic chemistry, thermochemistry, surfactant and macromolecule chemistry, and chemical process engineering. We have 80 researchers in this research center. And then this is Research Center for Polymer Technology. We have 4 research groups, polymer composite, functional polymer, polymer synthesis and modification, and green and sustainable polymer. In this research center, we have 35 researchers. So next, research center for quantum physics. So in this research center, we have the research not only in theory, but also in experimental. We have 5 research groups here, including high energy theory physics, nuclear and particle physics, and quantum matter theory, material design and simulation, and quantum device and technology. And finally, the research center for photonics, we have 3 research groups about the optoelectronic based control and measurement system, optical detection system, and process laser and spectroscopy. So in our laboratory, we have several characterizations, including the field of physics, chemistry, mining, metallurgy, polymer and materials, photonics, and quantum physics. There are the high performance computer in here, and also the lab of testing technology. The most of the laboratory are located in South Tangerang City. So there are several facilities here, XRD, and then SAM, TEM also, Raman, spectroscopy, and others like this. This is the basic characterization and material research. This is the view of the XRD microscope, EDS. And then this is the Raman XPS. We would like to install XPS in this year, maybe in the end of this year, this apparatus will enter our laboratory. And also high resolution TEM, this HR TEM from thermovisor will enter in the end of this year also. And this is some image of them. Yeah, and then several apparatus for chemical characterization. Yeah. Next, I would like to show you about the potential material research in our research organization. This can be extended to for synchrotron measurement. Of course, this is only some example, and in detail, typical research will be presented by the next panelists, Prof. Evi, Dr. Teguh, and also Dr. Suci. But allow me to show you several research activity in our research center that's maybe can be related to the synchrotron measurement. Yeah, the first one is synthesis of gold without mercury. This research is done by the researcher in a research center for mining technology. Yeah, we have several apparatus in here. And then also about the nickel processing and battery, research in battery. Several researchers from Research Center for Mining Technology and also from metallurgy and also from advanced material have research about this topic. And rare earth metal also, this is done by researcher and Research Center for Mining Technology. And this is the pilot plan for the rare earth processing. And also there are several research in functional material and composite. Mostly this research have been done by researcher in the advanced material, and also the material for energy, about the battery, also the fuel cell and hydrogen research. Lithium battery and supercapacitor, we have also research in this field. Magnetic and spintronic, I think Dr. Suci will present about this topic. And also research in biocompatible material. Yeah, catalyst, bioliquid fuel. This is also the one of important research in the Research Center for Chemistry. Yeah, and also research in molecular fundamental science that's have been done by researcher in Research Center for Quantum Physics and also Research Center for Photonics. They have research here both in the theory computation and also in experimental. Yeah, thank you very much. This is all of my presentation. I hope that this symposium will be a great meeting for us, for researchers to discuss about the potential application of synchrotron radiation on material researcher, and then this will open up new collaboration between BRIN and also SLRI and Konkan University. Thank you very much for your attention.
Thank you very much, Professor Dr. Ratna Nuryadi, from your presentation. It's quite interesting that we need to discuss more with the SLRI and then Kongkan University for the next collaboration research regarding about the material science and the accelerator technology, synchrotrons. So our next session will be we have 3 panelists that will discuss about the technology and application about accelerator synchrotron for in material science. There's 2 topics. First, is technology and application. Also, from Professor Nuryadi is about regarding about what kind of research center and also about research and development on the BRIN Institute. So we have 3 panelists: Professor Dr. Evi Kartini, Teguh Yulius Surya Pajaputra PhD, and Dr. Suci Winarsi. So because we have a lot of time, so I will give 25 minutes each panelist to discuss about these topics. You can maybe elaborate about the recommendation or suggestion of want to ask about the next collaboration research on material science application for the accelerator synchrotron. So first panelist, Professor Dr. Evi Kartini, the floor is yours.
Okay, thank you. Dr. Rifai. So first of all, I would like to thank to the committee and also greet to Dr. Busaya Korn, Sumacai, and also Prof. Ratno, and also Dr. Rohadi Awaludin, and all the participants. Okay, so I think that we have heard that from the 3 speakers that really important technology. I think the synchrotron is very important technology, yeah, especially to observe the material, yeah. It is, but since my background, it's more the neutron scatterer. So is it possible for me to share something here?
Yes, of course.
Yeah. Okay. So give me so just what I want to mention that between the neutron and then the X-ray, there are 2 tools that will be complementary to each other. Okay. Okay. So actually, I could say that the synchrotron is advanced material, yeah, technology. So the characterization, the neutron is also, yes, not like the normal laboratory scale material. Okay, so as you see that my background is mostly in from the neutron scattering. I grew up in in Germany and also in Canada, working at the nuclear reactor research. Yes, and then but recently I'm working on the material, which is mostly the lithium-ion battery material. So so the thing is what makes the difference between the neutron and the X-ray, right? So the neutron can be produced either from the reactor sources. Yes, the neutron will be the same, but only the way of they produce by the fission reaction. Yeah, from the reactor. We have the reactor Siwa Besi here, Indonesia, or from the spallation neutron source. Yeah, so this is using the pulsars and then giving the high energy neutron. Yeah, so giving very good intensity to observe where the material, the atom, and what does the atom do. Yeah, maybe in detail, Dr. Teguh will explain about the spallation. So when I return to Indonesia, I think that we cannot separate between the characterization, the advanced characterization with the laboratory, with the material characterization and the application. So at the time, I mean, we develop kind of integrated nuclear laboratory. So starting from the reactor, we have the several spectrometer, and then what we observe, yeah, we have the laboratory, the battery laboratory that we can develop the material and then observe observe the cathode, anode, or any kind of material, battery material. And then there is special why we need the X-ray, right? The neutron, yeah. Okay, so this is the collaboration, mostly on the neutron, but sometime I went also to the synchrotron, for example, the one in Japan. Yeah, we have the XAP, or also there is also diamond in ISIS, yes, beside the other spallation source. So if we do the scattering, so maybe in general there are two kinds. Either we do diffraction, the elastic, which is there is no changes in energy, or we do the inelastic scattering, so the dynamic, yeah. So what we observe, we observe many kind of the crystal structure during phase transformation in situ or etc. Yeah, and also depending whether you want to observe the surface, the inside, yes. And also the dynamic is mostly what they are doing when we give the energy. Yeah, so sometimes the phonon, for example, yes, we have to do the inelastic scattering. So what the difference? It's just the way how it looks. The neutron and then the X-ray, they have a different interaction with the material. Yeah, the neutron, since the neutron is have no charge, the neutral, but that has a spin. Yeah. So make it easier if traveling to the material. Yeah, it does not have the some reaction. Yeah, it will be different if with the X-ray. Yeah. So this is the Nobel Prize in Physics in 1994, showing that the show showing that where atom is and what atoms do. Okay. So this neutron, synchrotron, or electron, or a beam, so they have a different. I think that not all the instrument can show everything. So but they need to be to be combined. Yeah. So we can have the overall of this features, yeah, of what we are studying. Yeah. For example, this is the neutron, and then the synchrotron, as already explained by the first speakers. Yes, and maybe also electron beam. What we want to see actually is still the same. Okay, we want to see the material that cannot be observed by eyes. If we say that is the micrometer, we can still see by SEM, for example. Yes, by TAM. You can go further. Yeah, if beyond smaller than a micro or micrometer, going you to the angstrom, yeah, on a nanometer, you need a spatial tool. So this is why we need the high energy that can observe very small. Yeah, for example, the X-ray, this is in nanometer, and then you can go with the neutron or gamma ray. You can go to angstrom, even 0.1 angstrom. Why? Because all the atom in the crystal work on, in atom, the space, the distance between the atom in the crystal is in angstrom. So you need to see directly. So you need this, this particle, yeah, neutron or X-ray to observe this one. This is how the different interaction. Yes, in the neutron, you go directly into the nuclei. Yes, that is what the interaction and what makes the difference at the cross-section of the material. But in the X-ray, you see, you go to, because this electromagnetic interaction, you go to the outside. Yeah, to the outside, we call the layer. Yes, and then there is some reaction. What they see, it just so it means that even the object the same. Yes, but they will give different information. Yeah, here if you go, you see the straight line. This is the atomic number. Yeah, for example, the lithium. For the lithium, will be number 3. Yeah, in the periodic table. It's too small to be observed by X-ray. Yes, so. But with the neutron, it doesn't really matter, because the neutron will see that is have the negative 1.9 neutron scattering. Yeah, so this is what makes the two different. But toward the heavy metal, it's very good to work with the with the X-ray. Yes, but for the light atom, hydrogen, deuterium, for example, you need the neutron. Yeah, so this because you can see the like for example here the hydrogen negative, deuterium positive, so you can do the contrast. Sometimes it will be used for the application of small angle neutron scattering. Yeah, you can see the protein, and then you put the contrast to see the difference. Okay, so this is the different way of seeing. Actually, it's already explained by the first speaker. Yeah, it depending on which we call this the scale. Yeah, if we talk the neutron or the X-ray, actually the most important is the time scale or the energy scale. Yeah, time scale, or you can do the inversion to energy scale. Yes, or we do the space. Yeah, to Q factor. So this is what make different. Yeah, the small angle is the distance. Yeah, it's a more the nano. But if you go to wide angle, yeah, different. Different. Distance. Yeah, for real space, more smaller to go to wide angle or small angle. Yeah, depending on what we are working on. So this is also neutron versus X-ray. You see the same material, but they will see in different view. Yeah, this is the neutron and this is the X-ray. Yeah, and then if normally we do the refinement, it will give actually almost similar, almost the same between the X-ray and the neutron. Yeah. Okay, I will give an example of what we have done in the lithium battery. Yes. So in general, explained also by the second speakers before, what we want to see is inside the battery. Yeah, if you talk about the battery, the cell, it's called go to millimeter. But if you want to know inside the battery, we have to go to the nanometers. Yeah, we can still use the, for example, the small angle, the X-ray, and we want to do the more inside. Yeah, what the lithium does, we go to the angstrom. Yeah, so this is later on. Probably I give this information. Yeah, yeah. So we want to see what is inside the battery. With the normal X-ray, it is rather impossible to see because the X-ray just see only the surface. Yes, but with the synchrotron, as you have seen, you can observe directly also in situ. Yeah. With the neutron, of course, this is also easier. Yeah, you can put your cell and then you can study. So one of the example that we study is the electrolyte. Yeah, so we developed the solid electrolyte. This is very important because the important issue. Yeah, currently the important issue, because if you still use the existing electrolyte and separator, it's easy to to be there are some explosion. Yeah, if going to higher temperature, the explosion can appear. So we need to find a new material. So therefore, we develop the lithium phosphate. Yeah. So what we are studying, we developed this material. Okay, already patent, and then we work on the neutrons, both neutron and X-ray in Batam. Yes, with HRPD. Yeah, a simple way. Yeah. So. And then we do also X-ray diffraction in laboratory, yes, not synchrotron. And then you see the X-ray diffraction and neutron diffraction show different. Yeah, you know why? Because of they have different wavelength. Yeah, the neutron wavelength 1.8, but the X-ray is 1.5. Yeah, but we can put them together in Q space. So this is the refinement. So we obtain from both the neutron and X-ray. Yes, that is the you can see the left side is with the wavelength 1.5, and then the right side is 1.8. Yes, there is some a small scattering from the X-ray. Yeah, but we cannot see in the neutron. And then we do the refinement. Actually, the result will give the similar result between the neutron and the X-ray.
Another 5 minutes left.
Yeah. Okay. So we do the transform, and then what we can see here, it's the different what we can see, what we observe between the neutron and X-ray. So this is the left side showing that the X-ray because atomic number, but the neutron is the neutron scattering, and so we know exactly where the lithium is. So this is what we see, what the difference between neutron and X-ray. Yes, so we do all this characterization, and then for the other lithium iron phosphate also. Yes, so we can see the difference in the electron density map. So this is one example, and then further you can study also the the motion, the diffusion. Yeah, if you do the temperature dependent, and then anisotropy displacement parameter. Yes, of course, I'm sure that hopefully we can do also with the synchrotron, and then maximum entropy method to see how the energy or the motion, yes, of the atom. Yes, the lithium here in 3K, 100, 300, 400. Yeah, this done in Ansto. Okay, so we can also study about bond valence mismatch. So from this, we already make one publication. This is the joint with the group of Mr. Michael now from Devon University, and also MFD from Ansto. Yeah, I think I'm sure that if we combine this with the synchrotron, will be more information we can have. Yeah, this is one example. This is another publication, and then I would say also this is another maybe opportunity to study about solid electrolyte, the glass. Yeah, we can study the partial PDF. Yeah. Diffraction factor. Yeah, so this is another experiment for the glass using inelastic, and then the crystallization we can observe, and this kind of thing we can do with observe with the synchrotron. Yes, this is also showing the inelastic scattering from the JPAC instrument. Yeah, I think this is all some work. Yeah, okay. One thing I could say, one of the advantages of the synchrotron, because synchrotron does not need very high sample. Yeah, need only small, yeah, gram. So I think this is one of the advantages. So we can prepare more sample to do the X-ray instead. But for neutron, you need maybe for the inelastic, for example, you need 30 gram. Yeah, so a lot of work for that. Okay, so at last, as mentioned that Professor Ratno also mentioned about the importance of nickel. Now Indonesia the first producer of nickel, and it can be a very play important role to make the cathode. Yeah, there is some process from the nickel matte MHP and then become the nickel sulfate, cobalt sulfate, but of course we need mangan sulfate and lithium cobalt. And then this is showing that Indonesia, the first, have the largest reserve in the world. And then we have to increase the leveling the upper nickel, yeah, to become the cathode, yeah, to precursor cathode, because it will increase the added value. And then the more nickel, you can have the higher capacity, yes, but of course that's thermal stability. Yeah, so the people working now on increasing the capacity, yeah, by increasing the nickel content. Yeah, therefore nickel very important. This is for example, if you develop 811, so this is part, yeah. So many we can do the observe whether the anode or the cathode or the electrolyte or the cell itself. I think this is the good opportunity for the collaboration. Yes, in the near future with your group in Thailand. Yeah, this is I give an example, the local resources from the industry, and then we use the commercial one, and to do we make the precursor. So and then we show also with refinement. This is the X-ray actually, yes. And then 811 we develop also, and then finally we we make the pot shell or also a cylinder cell, and then we can study the charge discharge. But of course, this kind of study not only finish here. So with this opportunity, with the opportunity of collaboration with SRLI, I think very good. Prof. Ratno, I could say that we should work together with them. Yeah, because we don't have the equipment we can bring, and then facility, because as far I know about the preparation, the sample preparation can be made probably in BRIN, but when we can make also the coin cell or cylinder cell, but of course there is special treatment if we do the synchrotron. So maybe that kind of more technical, but we have to discuss. But from this meeting, mini symposium, I could say that very important to bridge, to do advanced characterization for all kind of material, actually not only the battery material, all kind of material. And then the second, that maybe we have to to put the list which one is can be ready directly to be proposed, yes, as a collaboration. Yes, I think that is the next step. And then as our chairman mentioned, that when there is a critical mass of doing need of this because I know the limited beam time in synchrotron, so I think why not Indonesia because a big institute, BRIN, so should also think about developing synchrotron in Indonesia. So that is my last comment. So we have to be ready with that. I think it's task for Mr. Rifai.
Okay.
To develop
Okay.
the synchrotron. Thank you.
Thank you very much. Okay, thank you very much, Professor Dr. Lfp Kartini. We still have another two panelists. I mentioned before, maybe perhaps the panelists will have a question to the keynote speaker that regarding about accelerator synchrotron. So maybe Dr. Teguh and Dr. Suci, we have like discussion with the SRI or Konkan University regarding about the application and also technology of the accelerator synchrotron. So the next panelist will be Dr. Teguh Yulis Surya Pacaputra. You have 20 minutes. Floor is yours. If you want to ask the SRI and Konkan University, Dr. Sungyat, you can do it right now. Okay, thank you very much. You need to unmute your Zoom.
Thank you, Dr. Rifai, and also thank you to our keynote speaker today, Dr. Wutikrai and Dr. Songyut, and thank you to Dr. Hadi and also Professor Ratno, and I think Dr. Bambang also come here today. So yeah, this time we already heard from our keynote speaker from Thailand, SLRI. First related to the synchrotron, and the second is related to the application, and especially in the field of battery research. So I'm thinking that we have a common work here. So as Professor Evi said, that it is a good chance to make a collaboration. So in this case, I would like to share some of my work related under the battery. Well, actually, I have similar work with Professor Evi, and mostly I use XRD and also neutron. So I will pass some of slides, but what I want to say that we can work in many different parts of battery. So my specialty is in the battery, so we can work from the material, the raw material, I mean for the component of the battery, and then the system of the battery, and then also we can work in the chemistry mechanism, and also in the scale, upscale, I mean, for the commercial cell battery, and also in package. We can work from the beginning until the end for the battery. And this is already known that for the battery, we have the cathode, anode, and also electrolyte. And we have many type of cathode and battery here and the application. And this is some explanation. It's already explained before. So I will pass this technique. This is very basic. And this is also already presented by Professor Evi previously. I have experience working at the JPAC Spallation Neutron Source, and of course, in our research organization, we have a reactor, and this is the difference of X-ray and neutron, as explained before. And this is some case. What can we do? And this, in this case, we can see the difference between when we use the X-ray and neutron. And then this is some work I do in JPAC related to the anode material of LTO. And this is some work that's related to the LMO cathode material, which maybe some of you know that this material is prone with the change in the oxidation states of mangan. It contains mangan 3 and mangan 4, and it is very, very sensitive and affected by the synthesis method. For example, we can use conventional, I mean, we mix the raw material only using the mortar, and we can use the chemical here. And one important thing is related to the content of oxygen. So in this case, we can see the oxygen deficiency. And what is the problem with the oxygen deficiency here? That after we examine the diffraction pattern here, for example, this is we use different raw material, lithium hydroxide here and lithium carbonate here, and we found that there are some oxygen deficiency here. But for the material which synthesized from lithium hydroxide and using mechanochemical and heating at 800, we can synthesize stoichiometric LMO here. And we would like to learn also what happens if we synthesize by different method, using different raw material and different method of mixing and annealing temperature. And we learn this structure at low temperature, from room temperature until 10K. So for the stoichiometric material, we found that oxygen occupancy here is full. But for this sample, we found some oxygen deficiency here. And when we learn by using low temperature neutron diffraction, we can see that mangan is here, can be grouped into two groups with a low bond valence sum and higher valence sum. So as we know before that mangan in LMO battery contain mangan 3 and mangan 4. And we found here that there are oxygen deficiency here. And this is what happened, and that with that synthesis method, we found what we call as a partial charge ordering here. And this is another work which I still work now, is that related to the LNMO battery. So we know that for this LNMO battery, there are two possibilities of space group, and it's still a controversy until now. First is FD-3M and also P4332. And we found that for the sample here, we are using yttrium as a doping material. For the sample without yttrium, there's a lack of, we call it the superstructure. But after we dope using yttrium here, we see some, if we enlarge, we see some superstructure here indicated by these peaks here. And this is the Rietveld refinement. And this is the lithium-ion diffusion pathway. And we also have a 2D MEM and 3D MEM. But I think one chance for our collaboration, maybe we can use a synchrotron here to gain, to obtain the oxidation state of some atoms here. So I heard before that in SRI that there's one beam with is under development. I think it's related to X-ray diffractions. Is that correct? Or we can use the already installed beam line, which can be used to determine the oxidation states, I think. So this is one chance for our collaboration in the future, I think. And this is other work. We study the battery using our HRPD in the Nuclear Research Center. And this is the diffraction pattern for the battery with the different SOC set of charge, set of condition. So we can see the how to say, the evolution of the diffraction peak related to the anode material, in this case is graphite. And this is the evolution in the diffraction pattern related to the cathode material here. And this is the work which I did in J Park in Japan for the in situ how to say, measurement using our battery. We make this battery in our lab. This is the pouch battery, and this is the cylindrical battery. And this is the results. So we can see for the charge and discharge, it's for 10 hours. We can see the different structure here. And we can see that some type of graphite here change, how to say, depend on the time of charge and discharge time. And this is for the cylindrical battery. Okay, so what I want to say that we actually have many chance to work together, because as the keynote speaker talked today, that we have a similar work actually related to the material, and of course with the other material. So let's open some collaboration and work together in this field. Thank you very much.
Okay, thank you very much, Dr. Teguh, for your presentation. But I'm like more want you to talk about want to have a question to the SRI or maybe the Konkan University. Maybe we have another our last panelist, and the next one will be have a discussion regarding about the collaboration research with the SRI and Konkan University. So I would like to invite the third panelist, Dr. Suci Winarsi, to have maybe we can ask something, or you have to have a statement regarding about the application of accelerator synchrotron in material science, something like that. So the floor is yours.
Okay, thank you, Dr. Rifai. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to thank Research Center for Accelerator Technology BRIN to organize this mini symposium. And also I would like to thank Dr. Hadi Awaludin, Dr. Muhammad Rifai, Prof. Ratno Nuryadi to give me a chance to present here. And also I would like to say good morning to distinguished Deputy Prof. Edi Giri, to Dr. Utikrai, Dr. Sungyot, Prof. Evi, Dr. Teguh, and all participants here. I'm Suci from Research Center for Quantum Physics BRIN. So as you know, this mini symposium is really important for us to make a research collaboration between BRIN and SLRI Thailand. My background study is about magnetic materials and superconductors. So I used to investigate the magnetic structure using muon spin relaxation. So I hope this collaboration can explore more and complete the information about the charge modulation and also lattice modulation in my sample, in our sample. So it can complete the measurement for each other. And okay, to ease our discussion, let me share my screen. Okay, today we are discussing about the accelerator synchrotron from its technique until its utilization in material science. So previous speakers already mentioned about neutron scattering and also XRD to investigate the properties of material. So in our study, we investigate the magnetic structure using muon spin relaxation. So this is just an overview. An accelerator synchrotron basically is an apparatus to accelerate the speed of particles. So from the previous speaker, they use neutron, light, and also electron to be accelerated. And in our case, we use muon as the particles to be accelerated. And the application is muon spin spectroscopy or mu-SR. So I will focus on mu-SR. Actually, this mu-SR and also neutron and XRD synchrotron can complete each other to reveal the magnetic and also crystal structure properties or modulation due to nanosize effect, for example. Because mu-SR can probe the uncover fluctuation rate. I mean, the fluctuation rate that cannot be covered by neutron and NMR, but can be covered by mu-SR. But also, in the contrary, the crystal structure modulation that cannot be covered by mu-SR can be covered by XRD. I would like to give a brief explanation about the basic principle of mu-SR. So basically, muon is accelerated and then implanted to a sample, and then the muon inside the sample will do the Larmor precession, and then the frequency of Larmor precession will equals to zero magnetic ratio times internal field. So the muon can feel the internal field of the sample. And then after 2.2 microsecond, the muon will decay into positron, and then it will be detected by positron detectors. And then it will accumulate as a time histogram, and the time histogram will be transformed into asymmetry versus time. So this is the data that we will get after performing mu-SR experiments. So currently the mu-SR facilities in the world, there are 4 mu-SR facilities in Canada, UK, Switzerland, and also Japan. So we used to perform experiment in UK and also in Japan. This is the muon facility in the UK. So we usually perform experiment here. He is my supervisor when I was PhD student, and she is my lecturer in University of Indonesia. So at the time she visited me in the UK. And this is muon facility at J Park. Actually, there are some ports here, mu-SR ports, depend on the material that we will perform. Okay, this is the briefly explanation about the characteristic of muon. So muon has half spin quantum number and it has magnetic moment. So these two properties makes muon can be a sensitive probe to detect the weak magnetism and fluctuating magnetism. For the charge, muon has class E charge and also the light mass of the lighter mass compared to the proton. So because of these properties, muon can be used to study hydrogen diffusion. And then muon spin has 100% self-polarized. So that's why we can perform perfectly zero field measurement, because zero field measurement is an ideal condition to study magnetic ground state. So what happened inside the magnetic materials? So if the magnetic material has homogeneously magnetic ordering, so the muon will do the Larmor precession like this, and then the asymmetry that we will get will be like this. So it shows the oscillation curve with the coherent amplitude. But if our sample has different or inhomogeneously distribution of magnetic ordering, for example, in the dark brown here, the dark brown represents the region where the sample has the long range ordered region, and the light yellow here represents where the sample has short range ordered region. So when the muon is injected to a region where has long range ordered region, it will do Larmor precession. But in the short range ordered region, the muon will just relax without do Larmor precession. So the asymmetry curve will not do the oscillation curve, but it will damp like this. There is a damping here. So the amplitude will tell us about the magnetic volume fraction. The frequency will tell us about the average local magnetic field, and the damping rate will tell us about the magnetic field distribution or magnetic fluctuations. So this is the example of μSR time spectra in our sample. In antiferromagnetic lanthanum 2 kappa O4. Lanthanum 2 kappa O4 has crystal structure orthorhombic, with the kappa atom is surrounded by 6 oxygen atoms. And we differ the particle size from 71 nanometer down to 24 nanometer to investigate the nanosize effect in antiferromagnetic. Let's focus on the 71 nanometer. So as you can see, there is an oscillation curve here. So it means the muon fill the long range ordered region. In the 52 nanometer, we can still observe the muon spin precession here, but there is a damping here. So it means the region of the long range order become decreasing due to the reducing the particle size, and it happened in the smaller sample. For example, in the 24 nanometer, the smallest one, the amplitude of muon spin precession just very small compared to other sample, and then the region of the short range ordered region becomes higher compared to others. So from this μSR time spectra, we can obtain that the long range ordered region happen in all samples, all nanoparticle samples, but the region of long range ordered region decreasing by reducing the particle size. To obtain more information from this μSR time spectra, we fit using this equation. So the first term represents the muon spin precession, and the second term represents the muon spin relaxation. And then from here, we can obtain the A1 and A2. A1 is an amplitude for muon spin precession, and A2 is an amplitude for muon spin relaxation. And then from A1 and A2, we could get the volume fraction of long range ordered region. And then the most important parameter is internal field of the sample. Okay, so this is for 4 samples with different particle size. And we can see that the saturated internal field or internal field at the lowest temperature doesn't change. So it's about 420 Gauss. But for the temperature where the internal field suddenly decreased to 0, it changed with reducing the particle size. As you know, the temperature where the internal field suddenly goes to 0 called by TN or nil temperature. So from this result, we can tell that the nil temperature gradually decreasing with reducing the particle size. Even if we compare to the lanthanum 2 kappa O4 bulk case, the bulk lanthanum 2 kappa O4 has TN is around 320 K. if we compare to the 24 nanometer, the Tn is around 30. So it means nanosize effect cause suddenly suppression in the nil temperature. And then to visualize the long-range magnetic orbit region, we assume or we propose the core shell model. So the core shell model here, the core is assumed to have the long-range orbit region, and the shell has short-range orbit region. And then the size core and the shell size, we could estimate from the volume fraction of long-range orbit region. So that's the spin dynamic and also spin interaction that we could get from μSR. And then the questions that are still left in our study is the charge or lattice modulation due to nanosize effect in magnetic materials, because we believe that there is not only spin structure, magnetic spin structure that affected by nanosize effect, but also lattice and also charge will be modulated due to nanosize effect. And then we also study in the phase diagram of superconductor cuprate. So for example, we study lanthanum strontium kappa oxide. So this is our study when the strontium concentration is about 0.20. So as you can see here, the mu spin precession doesn't observe because we cannot observe the oscillation curve. It's only show the Gaussian-like distribution or Gaussian-like curve. So it means the sample doesn't have long-range orbit region, but it still have static and randomly magnetic ordering. And then we investigate the nanosize effect by varying the particle size. And then what we could get from here that there is a rapidly increasing in the relaxation rate of muon spin. So it means there is correlation between kappa spin. So in other words, it means there is a magnetic correlation that developed at low temperature or below the critical temperature. So our study can contribute to the phase diagram of superconducting cuprate in temperature where the magnetic ordering happens. Okay, so this is our study, but as I mentioned before, we need to investigate the charge density wave or lattice and charge modulation due to nanosize effect. And then this is another contribution or another use for of μSR. μSR can analyze or determine the magnetic penetration depth. So from this μSR time spectra, it can be extracted the relaxation rate of muon spin, and then relaxation rate of muon spin. From here, we could estimate the magnetic penetration depth from by using this relation. And then μSR also can probe local magnetic field distribution in the mixed state of high EPC superconductor. So from μSR time spectra, it is transformed to local magnetic field distribution as a function of magnetic field. And then from here, it can be visualized like this. Yeah, so the red part represents the high distribution of internal of local distribution magnetic field, and the blue part represents the the lowest intensity of internal distribution field. And then this is contribution of μSR to study the superconducting gap. So from μSR, we can study whether the superconducting gap of our sample is S gap or D wave gap. Okay, so maybe I will go to here. So μSR also can be used to study the lithium battery. For example, this is one of example of lithium battery. So this is the μSR time spectra of lithium battery. And then from relaxation rate of muon spin, there is a king here, a king at high temperature and a rapidly increase in relaxation rate at lower temperature. So from this figure, what we can is anisotropic with transport confined to the lithium nickel plant at low temperature. And then exchange between lithium ion sites dominant at high temperature. So I would like to give to summarize my talk. So this is advantage of μSR that can be used to complete with neutron or XRD synchrotron, because muon is a sensitive probe to detect the small internal magnetic field. It's around 0.1 Gauss, so it will be able to detect the fields of nuclear. And then from the magnetic fluctuation rates here, μSR can cover the region that cannot be covered by neutron and NMR. And also μSR can be implanted, muon can be implanted into any materials, gas, liquid, solid, thin film, polycrystalline, and single crystal. For example, high temperature, low temperature, high pressure, irradiate with light, applied RF pulses. And this is another contribution of μSR. We can study the nuclear magnetic field of hydrogen, hyperfine interaction in semiconductor, determine interchain and intrachain charge carrier hopping mechanism, and study the properties of hadron. Okay, that's all my presentation. Thank you very much for your kind attention.
Thank you very much, Dr. Suci Winarsi, for your nice presentation. So we already have 3 panelists regarding about their research activities there is Professor Lfp Kartini and Dr. Teguh talk about the battery material that have material association with the neutron scattering, also in GPark. And Dr. Suci Winarsi regarding about μSR. So I invite Dr. Wuti Krai and Dr. Songyot to respond regarding about the research activities in BRIN Institute. And also we have Dr. Somchai in this joining webinar. Maybe Dr. Somchai I have a question regarding about the activities, research activities that can be collaborate with SRI or maybe Dr. Songyot with Konkan University. We have 50 minutes to have a discussion, so I invite maybe Dr. Mutikrai or Dr. Songyot or Dr. Somchai. If you have any question to our panelists, and maybe have a communication between Indonesia and Thailand, have a good collaboration in the future next, because it has to be the panelist asking to the keynote speaker, but in this case, maybe SRI may have a question to the panelists, what kind of facility or what kind of research activity that can be collaborated in the future, something like that. Or maybe the panelists have a question to the SRI Konkan regarding about your research activity. Maybe some part of your research can be elaborate more or using the Synchrotron accelerator in SRI, or maybe the collaboration research regarding about the battery materials research with the Konkan University.
Maybe
can
I ask question? Or?
Yeah, of course, yes, you can ask the professor.
Okay. First, thank you for this. I think this is a good forum to discuss what you have and what you done and what we have done, only partly. So the question is how do we start this collaboration if we never use the SRLI facility? Yes, that is the first. In terms of this joint research, I think it must be better. For example, the speaker talk about the battery materials, for example, can be our partner, collaborator. So it make easier, yes. For example, the sample from Indonesia made, and then what is the novelty, and then we discuss, and then they can take care, or how we start with this, because I'm sure that Mr. Rifai want with this symposium want to do the action, right? Yeah. Sure. And then normally the synchrotron or like the neutron source should be a proposal, right? Yes, we send the proposal, the time, and so for this collaboration, is that also will be applied for us or how? And what is the chance to get that? Okay, and then the next once we approve for this, to receive the beam time, and then what's the next? Is that the facility will bear the expenses or the accommodation or how? And then here also there is Professor Ratno, maybe can also help. What kind of with BRIN? Because I don't know whether BRIN also there are spare budget to do that. Some I think this is most crucial to start with. Yes, of course, if we don't have the travel budget, we can just send to the collaborator. Therefore, we need the collaborator there. My last question is this: there are some, this is about as far I know, not only preparing the material, but there's some specific equipment or devices, yes, to prepare the material. For example, a special experiment needs special, furnace, etc. Is that also available, or or shall we also develop in Indonesia? Thank you.
Thank you, Professor Lfp Kartini. So I will invite Dr. Wutikrai or Dr. Somjay to answer about the procedure, how to use the synchrotron and how can collaborate research regarding the application of synchrotrons and SLI.
Okay, so may I answer the questions? I'll try. Firstly, of course, by operating the synchrotron radiation facilities for over 20 years, one of the burdens that how to find the sufficient use from the user side to this facility, because it's a big facilities. And also, I think from the Indonesian side that you have the fuel reactors, the nuclear reactors. You found the same burden as well. Previously, if you mention its history, we try to connect or collaborate via the institute, like huge universities from Indonesia side, Batam side, Surabaya, the others. Cannot remember the name of all the institutes right now, but it's like the one-by-one institute, and this is quite, in my opinion, it's not stable. It's like a person via person's connections and then instituted link. So what it means that when the person to change the duty or change the research field, or just retire, something like that, the collaboration has been stopped. This year is a very fresh and good opportunities that we connect SRI to BRIN, which is a more stable organization and more policy concerned on about the research community things. So this gonna make us stronger and more stable in the connections between the collaborations. Of course, we open to all users to use, but you will find is that it has the difficulties to come to use somehow, which we try already that there shouldn't be any difficulties. For example, how to get started, right? If you're very familiar with the techniques you have or techniques you use for 10 years, to jump up to your synchrotron is quite a big burden. So actually, I would suggest, as we try to start it for a long time, that we breed up the new generations of young scientists there's no burden at all in use of the techniques, of the instruments, of the facilities among the countries, especially around ASEAN. That's what we try to set up the bodies called the LNSN, the Large Neutron and Synchrotron Facility Network. It's a kind of body that's attached with the COST, Committee of Science and Technologies of Southeast Asian countries, but it still be, the first few steps in the policy side, political side, the side policy side that we try to. But by that, I hope we will have more activity in the future to encourage young scientists and to let them know that there is no burden at all. Maybe in terms of school, in terms of workshop, in terms of things that they can travel all around in ASEAN and use facilities, our facilities, and these are their facilities as well. So I think that will increase a lot. I've seen a lot of research, a lot of samples, a lot of opportunities from Indonesia side. Why not? Just fractions of them come to Synchrotron. You will flood the beam time here. So I think the key word that I would answer is that we will try to train the new young blood with the opinion. There's no burden at all to use our and their facilities. That's to answer. Joint research and maybe the battery colloquiums of ASEAN is going to be interesting as well. Thank you.
Thank you, Mr. Sayapor. Yeah.
Okay, thank you very much for your answer. So maybe from the Dr. Teguh or Dr. Suci, you have a question regarding about what kind of collaboration in the future. So just now, Dr. Butikrai explained about how to propose some research activities to use the beamline or the beam time in Synchrotron or something like that. So is there any question?
May I?
Okay. Okay.
Okay.
Okay.
Ladies first. Please, Dr. Suci.
First. Okay, you can ask.
Ladies first.
Oh, thank you, Dr. Teguh. So Dr. Butikrai, I would like to ask question. Is it possible to, to measure superconductor or magnetic material samples? Because, for example, in our in my slide, I show that the question that are still left in our study is about charge modulation or lattice modulation modification as the temperature at high temperature or at low temperature and due to the nanosize effect. So if possible, we would like to measure our sample, for example, in your place, in your laboratory. So do you have suggestion for us if we want to measure our sample?
For the magnetizations for the magnetic material still be difficult for us because our machine is the old version. The light that produced from the machine is still be the polarizations in one direction. We cannot adjust it. By the new generation of undulator, somehow they can do the circular polarization of the light, and by that you can circulate the probe to react on your magnetic samples or magnetization direction sometimes. These kind of things situated in the Synchrotron in Japan, like Spring 8. I used to see the very nice work of a magnetic material that react differently when you circulate the polarization of the synchrotron light through the materials. We cannot do that right now, except we can do the indirect measurements. So somehow the magnetization change, we measure something else, but it's going to be difficult because, for example, you can see the work from the batteries research something already. Something change, structure change. Even though that distorted slightly change, we detect it we try to detect it. So it depends on the resolution of the measurements of the experimental setup that we can detect that slightly change. But for magnetically change, I doubt that structure is going to be that much change. So it will be better you directly measure the magnetic reaction. So you need the circular polarizations. But I used to convince the user like this. Why not? You try to somehow use our facility up the proper proposal to the bigger facilities like Spring 8, Synchrotron in Japan somehow. So let's use our facilities as a first step to develop proposal to the bigger facility. That's gonna get you the shortened time also as well. So that's about the magnetization things of material here in Synchrotron.
Thank you, Dr. Utikrai. So, how we can know the open for proposal? I mean, how we can know the information about the deadline or the date for open proposal?
Yes, all of this information that will be announced in our website, www.sri.or.th. I will type it in the chat rooms. The website all contain the technical information of all the techniques we have. Also the contact person of each technique, and also the channel to the online proposal submission. But I would recommend about on the talking to the right person. That's going to be the good first step. We found many users try on themselves to gain all of the information, build a proposal on themselves, and try to submit a proposal to us. And that takes so much time, too much time. So more shorten, you email to the person in charge of that technique, talking about your sample, your situations, what you want to measure, and he or she will convince you or give you information, convince you to change to the next person, and then you will get to the right person and you try to build up proposal with them. This is the shortest time, it's the more friendly time. Just only burden is that to start the first conversation with the person you don't know. That's difficulties, and that's just it. So I recommend that talk to someone in SRI. We are talkative enough, everyone here. So we like to talk to users. So please, and then keep up with the information about the workshop, about the school, about the thing we try to set up. Well, because of the COVID-19 situation, there's a good point as well that most of the things will be online. Like this, like this accelerator talks number 6 here. So there's a big opportunities to us as well. We never know that we can meet up few countries together easily like this. So please contact us.
Okay. Thank you, Dr. Utikrai.
You're welcome.
Okay, thank you, Dr. Suci. So I think from the Dr. Utikrai presentation slide, there's a email address that can you use for communicate with the person in the SRI. Okay, maybe in the next, Dr. Teguh.
Yeah, actually, my question is similar to Dr. Evi, Professor Evi and Dr. Suci. It's related about the technical and how we can do some work together and make collaboration. So I think first we have to establish some collaborations. It's paperwork, I think, and also related to the proposal. But more technically is maybe we can talk later about, okay, related to the diffraction techniques. So for example, like how much sample, what kind of the sample we can send and how we can send to SRI, and also the, how to say, the proposal. I think it's about that. Thank you.
Okay, thank you, Dr. Teguh. maybe from the SRI side or Kokang University want to try to elaborate some research activities, or what kind of setup that you need to improve for your facility to carrying some researcher from Indonesia, something like that. Is there any comments or suggestion or recommendation maybe?
Actually, previously we have some kind of programs to accommodate or help the users in ASEAN as well. So what we support is budget for the accommodations in Thailand along the time that you have the BRIN time. I'm not sure the budgets will be available next year, but it's going to be pretty the same. You can see that actually if by the negotiation in the level of institute, maybe it's just, you know, it's not the big numbers of money that we need. In our side, we can support something. In your side, you support the traveling cost or something, and then it's going to be, you know, convince the researchers to come across the countries to use some kind of the workshop. Even though the online like this, I think going to be the good convincing to the researcher, especially in Indonesia. You know, when I give a talk via the online or via the on-site in Indonesia, you are the biggest numbers of audience in every time that I give a talk. It surprised me every time, 300, 400, 200. It's a big one all the time. So we set up the big activity like this. We share the information of research you have. We share the techniques of the synchrotron we have. And then by fraction of successful proposal, it's going to be numbers that starting from 1 to 10, from 10 to 100. So I think we keep up like this. We're going to, you know, make it common to your size researchers that synchrotron is one of the two. I think that's going to be the most powerful things, you know, try to hypnotize them.
Yeah, that's true. This is good idea, I think. Yeah, is there any comments maybe from the panelists or questions regarding about the Accelerator synchrotron technology and application in material science? If not, I will invite the audience to ask to the keynote speaker or panelists maybe regarding about the technology and application in material science on Accelerator synchrotrons. Some of them already asked from chat room, but they already answered directly with Dr. Wutikrai and Dr. Somchai. So I think it's already done. So maybe someone want to raise hand or asking directly regarding about these topics of the webinar, mini symposiums. Is there anyone? If not, I have 3 questions. I usually ask this question to every.
Sorry.
Oh yeah.
I have question.
Okay, you can ask directly.
Yeah. From SLRI. Do you have any mail system for experiment, and also do you have what I can say a remote experiment so we can monitor from outside?
Good questions. Previously by the close collaborations, I mean, you know, if one of the person in synchrotron is a very close collaboration with someone abroad, they make the agreement to send the samples via email, via mail, the shippings, and person here do the experiment. That's kind of close collaboration like this. But the situation of COVID-19 in these 2 years, we try to open up the mail-in sample mode. That means after your proposal approved, allocate the beam time, you got the beam time. The scientists here will connect to you, talking about how to set up the experiment, what kind of sample, you prepare the sample very well, and then ship the sample to us. And we do the experiment for you. And then after that, we conclude the data. We send the data to the user. All this mail-in mode that's online like this. The thing is, after we did it for a year or two, it's come up like, I would say it's a bit of overload of our scientists, because, you know, we lack of the users come to try to at least prepare the samples in the proper way, discussion. So it's a bit difficulty. It's possible, but we conclude that after the COVID-19 pandemic, we would like to get back to the user mode again. So that means you can access to help us. Not only the work, you know, at the beam line, but the discussion, the rapid and on-time change of the setting of the measurement is also important as well. Of course, if everything going well, you can mail the sample in, and we do the experiment for you as a collaboration. But for the remote,
Recording in progress.
I just my jaw just dropped down like this. That's very nice, but we cannot do that. And I can say that we cannot do that in this 3 to 5 years in that level of automated system. So we still need to contact. We still need to talk, mail in sample somehow, and also come to Synchrotron. I would welcome all of you here. Thank you.
Okay, thank you. Lfp, is there any other question?
No.
To ask? Okay.
I mean, is it due to the rule or due to the technical problem for remote experiment?
No. There's no rules for a remote experiment. We do not have any rules to prohibit the remote experiment. Just only the complicated that you control everything. Talking about the beam lines, we control hundreds of the parts together, and the remote itself, the difficulty on itself to harmoniously work all of the parts, from the chapters, from the radiation, from the sample position, from the detector setting things. So I think it's too difficult for us now to set up this.
Okay, thank you.
Okay, thank you. Thank you for the question. So I will open other questions. Is there anyone want to ask from the audience regarding about the synchrotrons and application, and also technology? Maybe technology from the research center from Sato Technology want to ask. Maybe the young researcher can ask something regarding about the experiment, maybe the future roadmap or the future research activity, something like that. You can ask to Dr. Wuchikrai, and then also Dr. Kongkan from Dr. Songyot from Kokan University. Okay, we have 3 questions for Dr. Amy. I will read it for you. Regarding the components of synchrotron facility, bending magnet and insertion device, undulator and bigger, what is the characteristic of and the purpose of each component from beam point of view? Can we extract the beams from the insertion device? Maybe first question first, and then we can continue to the second question.
Okay. If you get back to my slides, we call it the characteristic X-ray of the device. So it's different. Most of the radiation, synchron radiation from the magnet, any magnet, will give you the curve like this. So we're talking about the width, the range from starting to when it drops, and the intensity on the y-axis, which is how much of the maximum intensity you will get, and that is intensity that's enough to detect anything that you want in the samples. So actually in the working range, it's going to be the narrower than that, because on the starting of this curve is too low of the intensity. In the end of this curve will be too low of intensity, so just one range. Even though the bending magnet gives you the big, long range with lower intensity of the light is produced. By the other insertion device like the undulator and wiggler is different. Undulators somehow is smaller magnet, but arranged in the series of alternatively north and south, south and north, north and south like this. So it produced the lower X-ray. So we call that normally it produces.
In progress.
So that's the kind of the characteristic of undulators. And then the wiggler, which is stronger, if you track back to the answer that Dr. Somchai answered previously, depends on the magnetic field, how much of the Tesla of the magnet. Yeah, so the biggest magnet we have here is 6.5 Tesla that will produce the X-ray up to 12 to 15, up to 20 kV. So that's curve, that characteristic curve. If you go to the insertion device, it's going to be narrower. If you go to undulator, it shifts on the left-hand side to the lower energy. If you go to the bigger magnet, if you go to the right-hand side of the high energy, but intensity is go up when you do with the insertion device because the magnetic field is more specific and stronger. But if you do with the bending magnet, it's lower and very broad. So that's like this. It depends on the design of the magnet. It's a new field as well. I haven't mentioned yet that our facility has a big project for the future to build up the next synchrotron source, which is about next 10 years in Rayong, the other province. It's a big project. We got the granted from the government already, but to build up this kind of big facility, we need time, we need a lot of work. Also the magnetic design, there's a new kind of thing as well. So our physicists use all of the knowledge in the publication from the conference in the advanced design of magnet and put it together, design the new kind of magnet here. So this is a kind of new thing as well. I would love if from the Indonesia side or the BRIN side come to concern participate in this new project. Why not? If you will have your own synchrotron facility in the future, why not you start to have your own beam line in our new facility? So maybe Indonesia beam line in our new facility to be the first step that to convince here this is yours, Indonesian properties, the beam line to do experiment and you come to use easily. So well, I think that's our answers for the first questions.
Okay, then second question will be, when we design the synchrotron, should we decide the exact number of beam lines from the beginning, or later we can expand the number of it?
That's a good question as well. When you decide the storage ring already, you cannot change anything. That's the point. You can come up with the other beam line. Maybe by the design, you can build up the branches of that port. For example, in our machine here, with one port, we can separate to be 3 branches. We have 6 bending magnets. Also, sorry, we have 8 bending magnets, 8 ports. By these 3 branches, the maximum number of beam line is 24. But now today we have only 12. So of course we have to design the storage ring exactly what we want for the next, I don't know, 20, 40 years, because we will not change the storage ring at all. The first step that we started the new project of the new facility is that we come across with getting the information of the user facilities, especially in Thailand, but also in Malaysia, in Singapore, in Indonesia, what techniques you want, what experiment you want, what's the energy range you want to be the information that build up the design report of the new machines. So the exact number of beam line maybe not, but exact number of the size of the storage ring, that's the must before we start up to build up the machine.
Okay, maybe the third question. In SPL, you have 12 beam lines and then 12 end station. What is the difference between beam line and the end stations?
Yeah, you can see by the charts that some of them are the same technique. So it depends on first what you want to do, what kind of experiment you want to do at the end station, and then it's come up to be okay, what techniques you want to establish in that end station, and then what you need, what kind of detector, what kind of alignments of the samples, and rotating the state of things, and then come up to be the optics of the beam light to deliver the light exactly match with your specification of experiment, and then you decide to do that. So that's come up. We have about 4 X-ray absorption techniques here. So it reflects the needs of the use already. X-ray absorption spectroscopy XAS community is the biggest community of synchrotron users right now. That's why we have 4 of them in line. Photo emission electron spectroscopy or microscopy, it's very difficult techniques dealing with the ultra high vacuum. Few of the synchrotron facilities in the world have this kind of beam line. We have 1. So the people who doing surface science using this technique. X-ray diffraction is one of them, which very popular. Everyone use it. Everyone. Most of the research institute has an XRD machine, but to use a synchrotron radiation SR XRD, it's going to be more energy resolution things, gain more deeper inside the structures. We have one here. So it depends on the user facilities that itself design or direct us to build up the technique to match them. We cannot build up the technique by ourselves that we need to have this technique, but no users at all in these 5 to 10 years. So we cannot do that. So that's why we have 12 beam line, 12 insertion, but less than 12 that the techniques of the use. Okay.
Okay, thank you very much for your answer. Okay, there's another question from Dr. Iwan Sumirat. How do you promote your facility to national and international new users? This is the first question. Maybe you can ask for. You can answer first.
Yeah. Like this kind of things, the talk, the seminar, the workshop. We have the level. We have a section in Synchrotron that correspond to the training, to the user promotion. We call the user service section. User service section has a task to dealing all the things with users, accommodate you, help you, support you from if you are the user allocated beam time already, accommodate you, give you the information, how to get to here, how to leave here, how to do the experiment here, and how to get back safely to your home with the good information. User service section also responds for the synchrotron usage promotion for academic side. So they do the training, they do the school, they do the workshop. So that's how we do promote the uses of the synchrotron facility in international and national level. Because most of these activities that I mentioned are in English. Okay, so if you keep up information you will match up with all these activities. But I would say, if we can go up, I mentioned it already. If we go up higher in the policies level, it's much better. Now we do like the person via person, institute via institute. But if like a BRIN via an STDA Thailand, something like that, you know, like how you call it, the body alike ministry. It's going to be stronger.
Okay. There's the second question. What is the percentage of or ratio between the senior and junior beamline scientists in SLRI? And then what is the recruitment mechanism for young beamline scientists?
Very good question.
Yeah, this
you know what? Well, what I was smiling is that it reminds me about 10 years ago when I first arrived at Synchrotron. It's all young, you know, new scientists. When we go out, the outsider, when they look at us, they say that we are the bodies, we are the organization of the young people. You know, like mostly 30s about that. But now, so the 10 years later, now I'm 40, over 40. So we're getting older, while the younger researchers are getting in the rate lower than 10 years ago, I would say. So it doesn't be the problem as well. We gain more experience, but this kind of facilities, we need the young blood, you know, the young that can work day and night, 24 hours things. So the ratio nowadays is less than 1, I would say. But in 10 years ago, it's more than 1 for the you know, junior to senior things. We're getting older every day. We need the youngest, but not for these facilities, but the new facilities. We need 100 of the young blood, young scientists, young researchers again. So there's a great opportunity in the area, I think.
Okay, thank you for the human resource plans. And this is the third question. Does SLRI has a commercial service besides scientific ones? If yes, what is the mechanism and then pricings? Maybe
yes.
How much to pay to use the Synchrotron's beamline, something like that?
Well, I have to quickly calculate it. Okay. According to what I mentioned, we have the user service section responsible for the academic users, right? We have another section called the business development section. Business development section concern on the users who are the commercial side. So what's the factors to differentiate these two kinds of users? It depends on the proprietaries of the data you gain from the experiment. If you heartfully open, you know, your experiment or your data, like in publication, in article, in PR things, this academic side. But if your data of the experiment is a secret, that's a commercial side. Via the commercial side channel, it will be charged of the beam time, and the charge is about roughly $400 roughly per hour. Depends on the project, so we have to evaluate the project first, how much of the beam time we need for these kind of things to solve gain the answers of your question in the commercial side. We do have many companies come to, you know, pay for this kind of channel, because what they gain, it has been proved already. What they gain, what they pay, and get the scientific answer for this kind of thing. If it hit to the point, they gain 10 times, 20 times more money in their production line. So by this kind of a business model, we have done already this kind of things. We also do the things called the total solutions. We tried about 5 to 6 years previously about how to promote the synchrotron to the industry like this. Go to talk, give the academic talk like this, and it's not quite work. So we come up with a new kind of things. Let's do the total solution. What is total solution? What you have problems in your production line, just tell the problems, and then we will evaluate and establish the projects, try to answer the problems in all of the ability we have with Synchrotron, and also connect with the other techniques, other machine, other labs, also in other countries as well. So this total solution we have, and it works so well. So yes, we have the commercial service.
Okay, thank you very much for your answer. I think quite clear about the commercial service in SRI program. Maybe we still try to adapt the kind of system in BRIN, I think. Okay, is there any question from the audience? We still open the...
Dr. Rifai?
Okay. Okay.
Yeah, I have a small comment.
Yeah.
Is it okay?
Is it okay, Professor?
So, yeah. Can you hear me?
We can hear you.
Okay, thank you so much, Dr. Wutikrai and Dr. Songyot. This is a quite good forum for us. We can explore in detail about the synchrotron facility and SLRI, and also we know about many potential research in our and then I agree about Professor Effie Cartini mentioned in her question that the important thing is how to start the collaboration. So my suggestion is if we can set up the further meeting to discuss more detail, maybe in that meeting we can identify the research topic, we can explore the possible partner researcher in BRIN and SLRI, and then maybe in that meeting we also can talk more about institutional collaboration, because if we have some agreement between, for example, BRIN and SLRI, so we can explore more possible opportunity, for example, possible matchmaking funding between SLRI and BRIN for exchange researcher about the mobility of researcher. This is my opinion. Thank you very much.
Mentioned before with Dr. Somchai, there's a three kind of scheme that we can use for come to SRI to use the beam lines, like visiting scholar, internships, and then visiting researcher also. But regarding about how we can start is we need to communicate first with the researcher in SRI about the technical problems and the technical activities on the SRI and then BRIN. So, but if we need, we can try to make another meetings regarding about this situation with the SRI management, with BRIN management also. So, is there any questions, comments? Maybe there's a Dr. Wahyu Bambang, the head of Research Center of Advanced Material. Maybe he want to give a comments or suggestions, or I'm sorry, maybe he already left the rooms. Okay. Is there anyone else to have a question or comments? If not, I have usually a question or question to the every keynote speaker in our webinar Accelerator Talk series. If we want to construct accelerator facility, what kind of accelerator facility we need to construct in Indonesia? And then the second one, if we want to construct a synchrotron facility, like Professor Lfp Catalyst explained before, maybe we want to conduct synchrotron 1. What kind of specification that we need to build to complement the SRI facility? And regarding about the human resource, this is our main problems about the young blood generation. This is quite a problem for our institute. How we can bridging the university student to want to learn about the accelerators technology and then become the scientist or the technologies scientists to try to construct the accelerator facility. And then the fourth question, what kind of specialization of the student or the researcher that to have to develop their knowledge, skills, soft skill, and then hard skill to try to develop and construct the technology accelerators in Indonesia. Maybe there's a 4 questions usually I have to ask to the keynote speaker. Maybe Dr. Utikrai can answer this one based on your experience with SRI.
Okay. Wow. It's a big things. Okay. Try thinking about it. First, you have to explore the needs in your market. That's the biggest thing. So before it's a top-down policies to do, you have to get the bottom up first. So you explore the needs, all the needs are gathering up, and then conclude it to be what's gonna hit to the audience first, especially in Indonesia, it's a big one. So I mean, for the Indonesian user, I try to mention both in the accelerator size and both in synchrotron size as well. For the accelerator size, it surprised me as well. The technologies go very quick, very fast, and then the accelerators it itself get more compact every year, and more applicable in the other way around. So to build up a body, a group of persons who capabilities of the accelerator design is a crucial thing as well. Also, the synchrotron facilities as well. That's why I mentioned to have a project that you will have a beamline in the other facilities. There's a first important step, and I think there's a good learning curve a lot to build up the new human resource about these technologies, and it use much less numbers of money of the budget you use, maybe 1/10 or less than 1/10, let's say, and 120, 150. That to build up beamline. The beamline costs about less than $1 million, less than that. But the whole project maybe cost you hundreds of millions of dollars. So build up the beamline. By that, to make it solidify, you will come up with a lot of plans, and also the human resource plan as well. You need about, to come up with the beamline design and build it up, you need about 20 to 40 people capable of working together closely. There's a big number already. Not mentioned about the student that go, forth and back to do the dissertation, to do the thesis about that. And then you operate it via the beam time that's going to be come up to Indonesian communities. I think that's a good first plan. Then you can evaluate again what kind of machine you need in the future. I think this is the quickest one. We used to plan to build up a beamline in Taiwan light source as well, or in Korean light source as well. but the project has been suspended because we get the signal of the budget of the new machine prior. Otherwise, if we didn't get this budget to build up the new machine, we will go for the policy to build up the beam line in the other better facilities. That's things.
Okay. Thank you very much for your answer. It's quite important for us to try to make a roadmap regarding about the asset technology action plan in the future, because we have a short, medium, and long term, and then the long term have to be synchrotrons like CLRE1. So maybe we need to prepare our human resource and for preparing for there to construct the synchrotron and other asset technology facility. Okay,
maybe Mr. Rifai, well, concerning about this, I think Mr. Utikrai mentioned before, well, that is the long-term agenda. I think it's good, yes. So I think first that we should involve this young generation to do actively with the synchrotron. That is the main, yes. And then the other side that to make it practical, not the scientists, the instrument scientists, probably a good idea if Indonesia can have a beam line, Indonesian beam line in for example in SRI. So that is normal like that starting, and then while we are planning to build up our own. That is maybe some suggestion. Thank you.
Yes, thank you very much, Professor Dr. Lfp Catalyst. Yeah, actually we have a program, a double degree program, and also some kind of collaboration with SUT in the future, because regarding about the how to use the SRI of the facility, SUT can be contribute to use that one, and then we can send our student and our researcher to study in SUT and then use the SRI facility, something like that. Yeah, okay. We still have another 30 minutes. Is there anyone to ask? This will be our first series for mini symposium regarding about the material science. The next week we'll have a life science section. So is there anyone want to ask from the audience, maybe from the panelists? If not, then I return to the MC for the next agenda. Dr. Amy?
Okay.
Okay.
Yes, thank you so much to all of the speakers, panelists, and also Dr. Rifai as a moderator. We have had a very productive and inspiring time together. I hope you have found the discussion in the symposium are informative and helpful. Okay, so now we move to the last session of this symposium, which is we will have a summary and also the closing statement. So for that, back to Dr. Rifai again, please.
Yeah, thank you, Dr. Amy. Actually, Dr. Rohaji Awaludin have a meeting with some industry about the cyclotron, so I will try to closing this agenda today. So I would like to thank for Dr. Utikrai and Dr. Songyot for your presentation, lamps, and like the application in regarding Accelerator synchrotron in the future. So in case of our research center, we try to get some more knowledge regarding about the accelerator technology, what kind of technology that we need to provide in the future in Indonesia, because we still have three kind of accelerator facility. We have a cyclotron 13 mega electron volt, try now to develop, maybe next year will be finished. And then we have another facility, synchrotron in Serpong, 30 mega electron volt, but still need work about it. And we have another electron beam machine in Yogyakarta and also in Bantar Ion that we need to more improve regarding about the utilization also. And then I can know that users community is much important right now to try to gathering about how to use the accelerator facility in case of this, in case of our webinar today about synchrotron's application. And this is have to be two series. Maybe next one will be explained by Dr. Amy. Now today is about material science, and then the next week will about the life science. So once again, I would like to say thank you to Dr. Utikrai, Dr. Songyot, and then three panelists, Professor Dr. Lfp Catalyst, Dr. Teguh, and Dr. Suci, for your joining our webinars. We hope maybe Dr. Ratno already mentioned, Professor Dr. Ratno mentioned before, we hope there's another meeting the next meeting regarding about the details about the topics, research topics, and then research activities that can collaborate in the future with SRI. And then hopefully we can try to contribute more in theology section. So I hope the user in BRIN Institute can come to SRI and then try to make some research activities there. And then now I'll try to close our agenda today. So I return to the MC, Dr. Amy.
Okay, thank you so much, Dr. Rifai. Ladies and gentlemen, we are now at the very end of this event. And on behalf of the committee members, I would like to express my utmost gratitude to all of the distinguished speakers, Dr. Utikrai, Dr. Songyot, and also Professor Ratno, all of the panelists and participants for making this symposium run smoothly. And we will also have the second symposium that already mentioned by Dr. Rifai. It's about the Synchrotron technology and the utilization in the life science. It's still in a collaboration between SLRI and also BRIN, in this case, the OR Hayati. So please don't forget to mark your schedule and please join us next week. That's all, and thank you so much for your attention from the morning until the end of the session. And once more about the certificate, we will already provide the certificate and we'll send to you all to emails that you have filled in your attendance list. And that's all from us. Thank you so much and see you next week. Assalamualaikum warahmatullahi wabarakatuh. Thank you so much and bye-bye.
Thank you. Thank you so much.